more general types of regions. And the way I did it was introduce these two types of regions, right? The type 1 regions, where these are the regions in the xy plane that we can place between two values, two constant values of x, so in other words, two vertical lines in the xy plane, so x equals a, x equals b, and then place the bounds on the y variable as just two continuous functions of x. Okay, and so we end up with these type 1 regions always being representable in terms of that nice set notation that I'm so fond of, and then from there we can apply Fubini's theorem by writing out the bounds, writing out the iterated integral, that is turning the double integral into an iterated integral, and we can just read off the bounds of integration. And we do a similar thing for the type 2 regions. Okay, but today's lecture's, well, I guess you could say it's about interchanging the order of integration, but it's really about realising that when we're given a double integral, okay, it's great that we have a Fubini's theorem for more general regions, but the principle here is that now we have a choice, okay? We can either use type 1 or type 2 regions or to apply Fubini's theorem to turn the double integral into an iterated integral. But also it might happen that sometimes we might only have one choice. And so I just want to make you aware of these possibilities. I'm not going to go into too much detail, but it may happen that in some cases, for some functions, and I'll give you a few examples later on in the lecture, it may happen that for some functions we simply cannot integrate it one way. All right, I'll explain more about that in a minute. But okay, let's just, I guess, revise what we mean by type 1 and type 2 regions. And here's a very good example to demonstrate this. So we've got an example here. Let's find the volume under this surface, right, called a paraboloid, that's of the form z equals some function of x and y. All right, so I'm thinking find the volume below a surface of that form. I could use a double integral. All right, so in this case, find the volume under the paraboloid z equals x squared plus y squared, and above some region D, where I should say this region D is in the xy plane, where D is bounded by the parabola y equals x squared and the straight line y equals 2x. Okay, so the question says do the problem twice. First by treating the region D as a type 1 region, and then by treating it as a type 2 region. It turns out in some cases regions can be both type 1 and type 2, and we'll see this is a prime example of that. Alright, so look, to apply Fubini's theorem, I need to work out what the bounds of integration are going to be. Alright, and to work out the bounds, I think in this case it's useful to draw a diagram of the region of integration. Alright, so let's see, the region D in the xy plane is bounded by this parabola. So there's the parabola y equals x squared, and the straight line y equals 2x. So here's y equals 2x, and so here we can see we've got the region D lying between those two curves in the plane. All right, so the strategy here is that we'll work out our volume. All right, the question says find the volume under this surface and above this region in the xy plane. So our strategy will be to evaluate the double integral of this function. So remember, the surface is of the form z equals some function of x and y, and that function is x squared plus y squared, and so we'll integrate that function over the region D. Remember, in these integrals, there are two important bits of information. One is the function we're integrating, and the other is the region of integration. Okay, so the first case, for this example, it wasn't too difficult to work out the function, all right, because we're given the problem, find the volume under this surface, z equals x squared plus y squared. We know we can use a double integral to find the volume below such a surface and above a region in the xy plane. But the bounds of the integral will correspond to, or will depend only on that region. All right, so now that's the plan. So what we have to do now is work out how we can apply Fubini's theorem as a type 1 region. So remember, the type 1 regions are the regions that put constant bounds on the x variable and then put the y bounds between two functions of x. So that's what we'll start with. All right, now what I need in this case, clearly, is to work out these points of intersection. All right, work out the points where these two curves intersect. Because that's going to be, well, that's going to at least give me this information of what the bounds for x should be. So the points of intersection I can obtain just by setting x squared equal to 2x. All right, so there are two possible values. This is a quadratic in x, right? So there are two values. One is 0 and the other is 2. All right, so I can, x equals 0 is the y-axis, so I expected that from the graph, and over here we've got x equals 2. All right, so as a type 1 region, I can write out this expression for D, the region D in the xy plane, as the set of all points x and y, and now I can place the bounds on x, the constant bounds on x. So I'm only interested in values of x between 0 and 2. Right? And just specifying that information only says that the region I'm interested in lies somewhere between the y-axis and that vertical line x equals 2. Right? To completely nail down the region D that I've drawn there, I need to give some extra information, and that will be the bounds for y. So just remember how we did this last time. Okay, for every value of x between 0 and 2, okay, or you can think of this in terms of Fubini's theorem and approximating the volume in terms of slabs. But for every value of x between 0 and 2, what you could do is draw a vertical line inside the region and see, well, what's the lowest value of y on this vertical, on each of these vertical lines. And each case, you can see that the minimum value of y will always lie on the parabola, all right, which has equation y equals x squared. So y equals x squared will be the lower bound in this case. And then the upper bound, you can see the maximum values of y corresponding to a single value of x in the range from 0 to 2. They will lie on the straight line which has equation y equals 2x. So that's going to be the upper bound in this case. All right, so now we've got an expression like this. Now I can apply Fubini's theorem. Okay, so then we've got the double integral that we're using to work out the volume can now be turned into an iterated integral. All right, so an iterated integral of the function x squared plus y squared. Now, because I'm treating this as a type 1 region, it means the corresponding order of integration is first with respect to y and then with respect to x. So first with respect to y between these two functions, x squared and 2x, and then with respect to x between 0 and 2. All right, so we've got an iterated integral. Remember, we work from the inside out. So integrating that function partially with respect to y will give us x squared y plus 1/3 y cubed, and that's evaluated from y equals x squared to y equals 2x. All right, this is just like a regular, treated like a definite integral of a function of a single variable. So in this case, we're treating x as a constant when we integrate. All right, so now it's just a matter of substituting in the bounds. Actually, I'll just write just one more expression. So substitute in that upper bound. We'll end up with 2x cubed plus 8 on 3 x cubed, and then minus the expression obtained when we substitute in that lower bound, so which is y equals x squared. So we'll end up with x to the 4th plus 1/3 x to the 6th being subtracted, right? And then that's all being integrated with respect to x. So it's just a polynomial in x that we end up with, and the result is 216 over 35. Okay, so just let me put this on the other screen. Because I want to refer to this diagram again. Now what we want to do is treat this as a type 2 region and repeat the process, see what it looks like, see how we could evaluate this as a type 2 region. Now remember, the type 2 regions are the ones that place constant bounds on the y variable. So in this case, as a type 2 region, we could identify just from the graph that the region lies entirely above the x-axis and below this line, right? Whatever that horizontal line is there. Okay, that's going to correspond to some value of y. Now we've worked out that the x value is 2, corresponding to that endpoint, or that corner of the region. And so when x equals 2 at that corner, y is equal to 4. All right, so this is going to be the line y equals 4. So now what we can do, right, we're placing the region as a type 2 region. We're going to once again write out an expression like this for the region, saying that it's the set of all points with coordinates x and y. But now we've worked out that we can give constant bounds to y and say that y lies between 0 and 4. So y equals 0 being the x-axis, corresponding to this point here. That's the minimum y value in the region D, and the maximum y value corresponds to this corner, which is at y equals 4. So now what we can, now this information here is just saying that the region lies somewhere between those two horizontal lines, right? But now we need more information to nail down that region. Okay, so what we can do is start drawing horizontal lines inside the region. All right, so corresponding to a particular value of y in between 0 and 4, now I can start drawing horizontal lines throughout the region, and I can see quite clearly that the minimum value for x on each of those horizontal lines inside the region always sits on this straight line. Okay, so that's the leftmost point on these horizontal lines, or the minimum value of x. All right, so I can see straight away that to write down the bounds of x, the lower bound is just going to correspond to the equation of the straight line y equals 2x. But I need to represent it in such a way that it's x equals some function of y, which is fairly straightforward. I just rearrange y equals 2x into x equals y on 2. Okay? But now we've also got a parabola. I can see that the upper bound for x will always lie on this parabola y equals x squared. Right? And what I want to do is represent that in the form x equals some function of y. But let me just make a note that when we have y equals x squared, so if I want to isolate x, in this case, the possibilities are y equals plus or minus x equals plus or minus the square root of y. Okay, but in this case, because we're only interested in positive values of x, we don't take the negative square root. Okay, so we can just point out at this stage that we don't take the negative square root since we're only interested in positive values of x, or non-negative values. All right, so that means then the upper bound will just be points on this parabola, y equals x squared, but expressed as x equals the square root of y. So I'll write square root of y as the upper bound for x. All right, so usually this is the process we need to go through in working out the bounds in order for us to apply Fubini's theorem. So that means then that the volume, which was that double integral I've written on the previous page, we can now apply Fubini's theorem and write it as an iterated integral of x squared plus y squared, where now we're treating the region as a type 2 region, so that corresponds to an order of integration. First we integrate with respect to x. Now the bounds are y on 2 up to the square root of y, and then with respect to y from 0 to 4. Okay, so remember it's an iterated integral. We work from the inside out, so now we first integrate with respect to x. Okay, so that's just going to be 1/3 x cubed plus xy squared, evaluated from x equals y on 2 to x equals square root of y. You can see when I substitute in the upper and lower bounds, I'm just going to be left with a function of y, so it's all making sense so far. Now, substituting in this upper bound, remember x equals the square root of y. I mean, maybe I should have written it as y to the power of 1/2. It might have made more sense in that case, because when I substitute it into expressions like this, so I'll have 1/3. So in this case, it'll be y to the power of 1/2 all to the power of 1/3, all to the power of 3, which will give me y to the 3 on 2. And then here I've got y to the 1/2 times y squared, which will give me a y to the 5 on 2. Okay, and then minus the expression obtained when we substitute in that lower bound. So that's 1/3 y on 2 cubed plus y cubed on 2. And that's all integrating with respect to y from 0 to 4. All right, and just check that we get the same answer as last time. All right, so the point here is that, all right, we've got these two different types of regions. Well, which calculation did you prefer? I don't know. It doesn't really matter, actually, right? But sometimes it does. So that's the main point, I guess, is that we have a choice now. We have a choice which order we can, or which order of integration we can use. All right, now remember, for the much more complicated regions in the xy plane, usually the approach is to partition it up into regions which are either type 1 or type 2. All right, and sometimes we may even be able to partition them up into regions that are both type 1 and type 2. So over each region we do have such a choice. Okay, but one point now. So I've just demonstrated that we do have a choice here, right? One point, though, is that what happens if we can't integrate a function one way? Well, what we could do is try changing the order of integration. So, for example, in this case, we're given an iterated integral to evaluate, all right, where the function we're integrating is sine of y squared. But now, where the problem just gives an iterated integral, right? It's sure there's a diagram here saying, well, this, from what we've seen, this represents the volume below the surface z equals sine of y squared, and above this region in the xy plane. So it's a volume of a solid. I mean, we can see from the diagram here that it's a finite solid, right? A finite region in 3 dimensions. But now the question is, how could we evaluate this integral? Now, in fact, it turns out that, I mean, we could try substitutions and so on, but we wouldn't get anywhere. It turns out this first integral with respect to y cannot be done, at least in the sense it cannot be expressed in terms of elementary functions. Now, what does that mean? Let me just direct you to a reference in in Stewart. Page 522, I think it is. There's a section entitled Can we integrate all continuous functions? And really what this question means is, can we write down the antiderivative of all continuous functions in terms of elementary functions? And so, what, you may ask, are elementary functions? All right, so these are the functions we're all familiar with. So, for example, the polynomials, the trig functions, exponentials, all their inverse functions, so the logarithms and so on. Now the hyperbolic functions, okay, all rational functions, so ratios of polynomials. All these are known as elementary functions. Oh, also, any of the, how many are there? 5 standard operations on these functions. Okay, so things like addition, subtraction, multiplication, division, that sort of thing on all the functions. Oh, the 5th one being composition of functions as well. Right, so all finite combinations of these on that list of functions I just gave, these are what we call elementary functions. Now it turns out some elementary functions themselves do not have antiderivatives which are expressible in terms of elementary functions. So these are sometimes referred to as non-elementary integrals. All right, so I'm just giving you some keywords here and I'm just providing some discussion on the topic. So another good question that you could ask is, given a function, so given sine of y squared, for example, as we did in this example, how do we know we can't write the antiderivative of that function in terms of elementary functions? Well, I don't have an easy answer for that, but there is an algorithm known as the Riesz algorithm, which is a decision algorithm. Right? It's a fairly complicated algorithm, actually, often implemented in all your standard mathematical software packages to decide whether or not a given function has an antiderivative that is expressible in terms of elementary functions. It uses a principle known as, or a result known as Liouville's principle. All right, so look, these 4 lists of things, I'm not going to say anything more about them, but what I'm giving you are just some keywords. I mean, you can go and read about these elsewhere if you're interested. Okay, but the purpose of me saying this, though, is just to make you guys aware that not every function, not every elementary function, let's say, has an antiderivative that is expressible in terms of elementary functions. All right, so some examples. So apart from sine of y squared, so I might as well list that, sine of x squared with respect to x. Also the cosine. Others are the exponential of a square, so e to the plus or minus x squared. In fact, I think any even power of x in that exponent would do the job. Some others, e to the x on x, 1 on log x. So all these functions which are easily expressible in terms of elementary functions, their antiderivatives do not have or are not expressible in terms of elementary functions. Okay, so one thing we can do, though, for example, consider this. If we're being asked to integrate sine of y squared in a particular order over a particular region in the xy plane, so in this order, so this one here, where we first have to integrate with respect to y, from y equals x to y equals 1, then with respect to x, well, One thing we could do is write out a Taylor series expansion for this. Right? It's one thing we could do. Write it as a sum of terms from n equals 0 to infinity. Now, in this case, what would that look like? Negative 1 to the n, y squared to the 2n plus 1 over 2n plus 1, and then just integrate each term, right? Because each term in that sum is just a monomial in y. Right? We'd end up with another Taylor series. But this is not what I mean by being expressible in terms of elementary functions. Right? That's just one possibility. I'll leave that as an exercise for you guys to work out what the Taylor series of the integral of sine of y squared is. However, what we can do, what was the title of this chapter in the workbook? Changing the order of integration in a double integral. So what we can do is try changing the order of integration to see what happens. All right, now let's just have a look at that integral again. So what I can do now as a first step is say, I'll refer to that integral as I, and just point out that because that's an iterated integral with respect to x and y, I can identify that through Fubini's theorem as a double integral. Okay, so I can identify that as a double integral of the function sine of y squared, and then I can say where the region D is expressible in this way, as a set of all points with coordinates x and y, and now I can read off the bounds from the integral, all right, and work backwards through this process that I've just been showing you. So now we've got bounds for y, or rather, let me start with constant bounds. We've got bounds for x, which are between 0 and 1. And then given those values of x, the bounds for y are from x to 1. All right, so I can draw a diagram of this in the xy plane. So what does that look like in the xy plane? So, just reading off the information from left to right, first of all, I have that the region lies somewhere between x equals 0, which is the y-axis, and somewhere between x equals 1, somewhere to the left of x equals 1, because 1 is the upper bound here. All right, so I know then that the region D lies somewhere in here, right, in this infinitely long strip for any values of y, but I need more information. So I need to cut that strip at y equals x, which is the lower bound for y. So here's the line y equals x, and then the line y equals 1. So now where does y equals 1 go? So where y equals x intersects x equals 1, at that point, that will be y equals 1. So the region is actually a triangle, right? And given like this, once again, for all values of x between 0 and 1, the y-coordinate of any point inside that region lies above y equals x and below y equals 1. So the region is in there. Okay, so now I can see that in this simple example, just to demonstrate this point, I can see that this could also be expressed as a type 2 region, right? This is it's a simple enough region, right? So it's expressible as a type 2. So, in that case, I'll be able to write out the expression for the region giving constant bounds to the y variable. So in this case, what can I identify as the bounds for y? Actually, I should have written y equals 1 up here. That's that horizontal line there as the upper bound for y. Okay, so now I can see the minimum value of y in the region is at the origin, so which has equation y equals, well, which lies on the line y equals 0, and the maximum value of y is 1. And so given those bounds for y, what are the bounds for x? So here's where I can start choosing a value of y between 0 and 1, and then drawing horizontal lines inside the region. Okay, and the leftmost points on these lines are going to give me they're going to correspond to the minimum values of x in the region. And you can see in this case that they always lie on the y-axis, which has equation x equals 0. You can also see that the rightmost points of these horizontal lines always lie on that line y equals x. Okay, these are the maximum values of x given a value of y, and so that has equation x equals y. Okay, so that implies that integral that we started with can now be applied using Fubini's theorem, but written in the other order of integration, just like we've been looking at just like we looked at in the previous example. So now first we integrate with respect to x, and I read off the bounds of integration here from the line above. So we integrate with respect to x from 0 to y, and then with respect to y from 0 to 1, right? It's an iterated integral. So now I don't have to worry about integrating sine of y squared with respect to y just yet. I first integrate with respect to x. Okay, so that's simply going to be x times sine of y squared evaluated from x equals 0 to x equals y. All right, now substituting in the upper and lower bound, so we'll have y sine of y squared minus 0, right? When we substitute in the lower bound x equals 0, we're just going to get 0. All right, now this is a completely different story, right? Now we've got to integrate y times sine of y squared with respect to y, completely different. So we could make a simple substitution here, right? And in fact, if you set u equal to y squared, du dy is equal to 2y, and so on. Use that as a substitution. So you can see here this y sitting next to the dy in the integral is proportional to the derivative of our substitution. So it's just perfect for using a substitution method, right? The point is we can evaluate it easily, right? And in fact, it just works out to be negative 1/2 of cos of y squared, the antiderivative of that function, right? And so that's now evaluated from y equals 0 to y equals 1. Okay, so that ended up being not too difficult, just substituting in those bounds. We end up with this expression. All right, so, hopefully you get the idea. There's just, there's one more. I guess I should come back to just those comments I was saying about these algorithms for deciding when we can't integrate these functions. Here's a list. If I were to, you might see in some past exam papers some questions like evaluate this iterated integral, and you'll see a sine of x squared or sine of y squared, or you'll see a cos of x squared, that sort of thing. Simple examples like that, so e to the x squared, e to the negative x squared, cos x squared, those functions, I would anticipate that you'd quickly realise that it's one of these examples that you can't integrate, especially if you spent 30 seconds trying to evaluate that integral, and then realise, oh, hang on, this must be one of those questions where you can't work out the antiderivative, where I have to swap the order of integration. Otherwise, if it was anything more complicated than that on the final exam, I'd be inclined to say the antiderivative of this function is not known. Okay, so using that information, answer this question, right? So I'd make it absolutely clear of what the goal of the question was. Okay, because I haven't spent time, and I'm not going to spend any time talking about this decision algorithm, it's quite complicated and, well, would go in a higher level analysis course, I think. All right, so look, just one more example. It's at this stage. I'll just add a little pointer at the bottom of the page here. And just say go to pages 62 to 63. I just want to demonstrate how it's not always as easy as it looks. Right? These two examples that we've worked through in the lecture today have both been regions, well, the regions of integration in both cases have both been type 1 and type 2. So it was very straightforward to switch the order of integration. But if we go back to page 62, and this example that's given, so I think this is where we were introducing the type 1 regions. Okay, so we were given this double integral and a description of the region, and now here I've got a diagram of that region of integration. Okay, we worked out points of intersection, worked out what the correct bounds were, and then applied Fubini's theorem, right? Treating it as a type 1 region. Now what I want to do is treat it as a type 2 region, or at least attempt to, and see what we can get. So I might just, I'll put this diagram over on the other screen. And I'll just say this is from, what was that page? Where do we come from? 71. So from page 71, just for convenience, I might draw up just a rough diagram again of that region. So y equals x squared, and we also had the line y equals x plus 2. Something like this. Okay, we worked out the points of intersection. At least the x-coordinates were -1 and 2. But now what I want to do is try and treat this as a type 2 region. So as a type 2 region, that means I need to put constant bounds on the y variable. So I can see here that the region I'm interested in lies above, so the minimum value of y is y equals 0, which occurs at the origin here, and the maximum value in the region occurs up here at y equals 4. So my inclination then, treating this as a type 2 region, would then be to say, all right, treat this as a type 2 region. Sorry, I'll make a note of that, as a type 2 region. So we'd write y is between 0 and 4. Okay, and now what was I doing before in order to work out the bounds for x? So I was drawing horizontal lines all through the region, right? So give me any value of y in the region, and I can start to draw horizontal lines there. So for example, down here, I can see where I'm drawing horizontal lines. The minimum value of x on those lines always lies on this left part of the parabola y equals x squared, and the maximum always lies on this on the right part of that parabola. Okay, so I'll keep drawing these horizontal lines, right? Oh, look up here. The upper bound is still on the parabola, but the lower bound has changed. So at some point, at some value of y, as I move up through the region, the lower bound changes from being on this left branch of the parabola to being on this straight line. At what point do they change? And I can see, well, it's whatever that value of y is corresponding to x equals -1. So I might draw a more pronounced line through there and say, well, what will that be? X equals -1 on that line must be y equals 1. right? So here I can draw question marks and just say, well, writing this as one expression doesn't make sense. All right, so I can't write it as one expression. Instead, what I'm going to have to do is treat it as two smaller regions. So instead, let's call this region below y equals 1, I'll call that D1, and above this line, I'll call that D2. All right, so D1 is then going to be the set of all points with coordinates x and y such that y lies between 0 and 1. And then the x bounds are, well, the left branch of this parabola. So remember from before, I was explaining this before, was it the same? Yes, it was the same parabola. How convenient. So y equals x squared, right? I want to rearrange this and write it as x equals, well, plus or minus square root of y. But the negative sign gives me the left branch. That'll correspond to the negative values of x. Right? And the positive square root will correspond to this right branch. So clearly the bounds for x then will be negative square root of y and positive square root of y, at least for D1. Now for D2, those are the values of y between 1 and 4, right? So above here, and that's where the lower bound for x will change. Okay, so the upper bound will still be the positive square root of y, right? That's the right branch of the parabola, but the lower bound, okay, the minimum values of x on these horizontal lines will correspond to the line with equation y equals x plus 2, or in other words, with equation x equals y minus 2. All right, so now we've got the region that we started with, D, as the union of these two regions, D1 and D2. And this is where we can use the properties of the double integral, right, where the double integral over that region D is just the sum of the two double integrals over D1 and D2. All right, so remember, I'm treating this as if it were a type 2 region, right? I mean, say the integrand was not 4x plus 10y, as in the example. All right, what if the integrand was something like, again, sine of y squared, right? Then I wouldn't be able to do that integral in the first order, so I'd have to swap the order of integration. Okay, so you get the idea, right? Now we can, or actually what we have is an identity of iterated integrals. So that implies, what was that, the iterated integral that we ended up with from that previous lecture, as a type 1 region, treating it as a type 1 region, we ended up with this iterated integral, 4x plus 10y dy dx. But now we've worked out, if we want to change the order of integration and treat it as a type 2 region, we can't treat it as a single type 2 region, but we can write it as the union of two type 2 regions. And then applying Fubini's theorem to both of these double integrals then just gives us the following. All right, so for D1, we first integrate with respect to x from negative root y to root y, then with respect to y from 0 to 1, and plus the second integral will be integral of 4x plus 10y, first with respect to x. So now I can read off the bounds from the second expression. So lower bound is y minus 2, upper bound still root y, and integrating with respect to y from 1 to 4. Okay, so there's an identity there of iterated integrals. I mean, I won't work through them, but the point of this exercise is that we're not restricted to just working with type 1 or type 2 regions, okay, depending on, I mean, depending on what the region is, doing it one way will be a lot easier than doing it the other. As you can see from this example, if you can do it as a type 1 region, then do so. But if you can't, because you can't evaluate the integral, try swapping the order of integration and evaluating it in the other order. You always have that option, even though sometimes you may end up with a much more complicated expression. All right, cheers guys, I'll finish there.